All right, so it didn't actually give you the time, the accepted time for the vertical launch. Now, if you recall from lab 4.1b, you used the horizontal launch. We measured out the horizontal distance, the range, and the vertical distance, the starting height. And from those, you were to figure out the VI of the rocket. And then with that VI, go backwards and predict how long would it take for this rocket, when launched vertically at that same VI, to go up and come down, total time. So what you didn't realize at the time of the making of this original video was that I was recording the time in the camera, and we would later come back and check it. So here's the video in real time. It's Kyle pumping with those slick socks. There it goes. It's up. And it's down. Okay. So if we come back over here, this program actually is pretty nice. They count the frames for us over there. You can see in the bottom corner. And let's hide the tools so we can see the time. Basically, as soon as we see this thing take off, it's a little hard to get it exactly. Right around, maybe there, when you first see that motion. So we're talking about somewhere around, say, 4.45 seconds. It's down here in the lower left, frame 268. And it goes up. And it comes back down. And let's frame by frame it. Here it comes. Lumpy making an attempt. There it is right here on the screen, the middle. Dropping down, and it seems to hit there. See, it hits, and then the next frame it doesn't move. As it turns out, it hit a step, so that's higher than it was launched, but that's okay. So our time there, it seems like it touched down at 10.17. So if you subtract those two, 10.17 minus 4.45, you can check my math, but let's see. 4.45 would take 5.55 to get up to 10, and another 0.17, 5.72 seconds is what it seems like to me. Now, 5.72 will be your accepted time for the actual vertical launch. And so when you do your percent error, do the time that you calculated minus 5.72, whole thing over 5.72 times 100, you get a percent error. Now, that percent error is interesting, gives us a sense of how close we are to the accepted magnitude. However, it is not perhaps how you've done in the past, the way you determine solely whether this is a decent or valid or successful experiment. So you can't just say, oh, look, we're within 5%, or you probably are within 5%, so it's good. That's kind of an easy way of getting around the issue of uncertainty. What we're trying to work on here, which I know is clunky because it's the first, second time you're doing it, the uncertainty determines whether it's a valid experiment, whether the results actually are verified. So what we have here is you get your percent error, and you're going to use that as a comparison point. The full version of this, we would have you comparing percent uncertainty to percent error. But we're going to stop a little short of that because it's a little easier for us right now. We're just going to see whether, with our range of uncertainties, whether that 5.72 and its uncertainty, whether they fall into alignment with each other. If they do, verification. If not, not. Okay, so notice there's definitely some uncertainty in this video. One of the pieces of uncertainty here is the landing. It's definitely not landing at the same height as it started, or at least it doesn't seem to. It hit a step. So how many frames might we be off? Well, maybe it'd only be one more frame for it to get back to ground level. So maybe we're off by one frame on this end. And then if we come back to this end, this one's also very hard to catch that first frame. So, it seems like maybe we're not off by a full frame. Maybe we're only off a half frame or something. So basically, you can say that our measurement here with the video is off by plus or minus 1.5 frames, something like that. And the way you can do that then is 1.5 frames. It's a 60 frame rate camera. So 1.5 divided by 60, it's actually a fairly easy number. It's 15. 1.5, move the decimal. 15 divided by 60 would be 1/4, so 0.25. So 1.5 divided 60 is going to be 0.025. So basically our accepted range of time for the actual rocket measurement is going to be 5.72 plus or minus 0.025. So, you could do a little rounding in there as well. So basically you're getting down to about 5.695. You may just have to round that to 5.70. And as high as 745, and then round that up to 5.75. So that's going to be your accepted. And you have your range of possible times there based on your uncertainty calculation that you did. We started in class and hopefully you finished via the video. So if those two overlap at all, the ranges, if they overlap at all, then you have a valid or verified experiment. And you have to make that statement. If they don't overlap, well, then you don't. You have not verified, or you have not gotten what you call an affirmative or positive result. But I have a feeling they're pretty close. Whether verified, we'll see. You got to look at your numbers. And you also have to go back and look at your uncertainty. But anyway, that's it. So for you, you're stopping with that range of uncertainty that you figured out with the times based on all those numbers we were running in class. See if that overlaps with this 5.695 or 5.70 up to 5.75. Any overlap, you write it there. The range of uncertainty and the actual time overlap, so we have verification. If not, then no. All right, that's that. The real question is, how do I stop the recording? There we go.